Hi, folks. Today we'll talk about a very important concept in computer science, mathematics, as well as life. Yeah, the concept is that of abstraction. So, what really is abstraction? I'd like to keep this video informal. So, I'd like to define it as the ability to forget details of a concept and use its name for referring and for building further. Okay, so let's explore what do we really mean by that. So let's say we have a computer screen. Let's say this is the computer screen that you are viewing right now. So what really is a computer screen? It's a sequence of dots, right? Each dot is called a pixel, which is a short for picture element, and it has its attributes, which includes its color as well as its other attributes. For the sake of discussion, let's say it's just a dot which has a color. So at any given point in time on the screen, let's say you are seeing the picture of a man, uh, something like this. What really is this? This is a sequence of pixels, right? Nothing more. But over here, we can only view this because we perceive it not as individual picture elements, that is pixels, but what they represent as a whole. Starting from here till the end of the frame, current screen, there's, excuse me, these are all pixels, but and yet we see something on the screen. So let's say now imagine you are watching a video on your laptop, on your mobile. So what really is happening in the video? What you have is a sequence of frames running at a certain frames per second speed. So what does that mean? What that means is that you have to, what do you have there, right? So this is a single frame and you extend it in time. Let's say this is frame one. So after that you see frame two at time two. After that you see frame three, so on and so forth. It's a sequence of frames, right? So, but what really is happening is that at this point in time, you have a concept called a pixel. It's a picture element. As long as you have a number for it, you have its attributes. That's all you care. You build these pixel elements, pixels, without thinking about how do they render, what they are, what are their details. And then you make a larger building block, which is called a frame. This is one frame, or one picture, as you might like to call it, right? So now this frame is another building block. This is also an abstraction, just like the pixel here. This frame is also an abstraction. So what do? You make further frames. You don't think now that you have a name for it. There is a thing called frame, which constitutes of different other things, which are called pixels. Pixel is an abstraction, a frame is an abstraction, and you use this concept of a frame to build another abstraction, which is called a video. What really is a video? Whatever you're watching, if it's a movie or even this video is just a sequence of frames, right? So as long as you have a name for another abstraction called frame, you build on it. So I guess you get the common theme. The common theme is you build on concepts, right? So you have over here, if we make a layering of concepts with respect to the example that we just saw, you have the concept of a pixel, right? And you use that concept to make another concept called frame. But once that concept is made, you don't bother by the details of, whatever concepts lie underneath. And then you can use this concept of a frame to make a higher level abstraction. What we mean by higher level is an abstraction that uses frame to build other things, right? So a video is a sequence of frames. So this is a sort of a layering and stacking together of abstracted concepts to build things, right? So what we're doing here is that we are building things. And how exactly are we building them? We are building by making abstractions. All right, so this concept is very similar in real life too. So let's think of something else. So let's think of what we have in mathematics, things called functions, right? So in maths, you have functions. Let's say if there is a single variable function, f of x is equal to whatever, 2x plus 1. So what really is this? What is this? This function f of x, what is this really? It's nothing else but an abstraction because it's not out there anywhere, right? It's all, this is a concept, right? But it's a useful concept. Why? Because we can use this concept to do other things. For example, we can compute its value at various points, at various, concrete values of x. Let's say for x is equal to 1, 3, and 5, we know what f of x would compute. Moreover, we can build f of x to make other functions. Let's say we have another function called g of x. It's very typical in mathematics. You build on top of existing abstractions. So uh, let's say it's a derivative function. Let's say it's d by dx of f of x. So, we have this thing called a function, which is an abstraction. This is how we define it. And we use it to build another abstraction, another function, right? And this is how we define the new abstraction. So this again is another way to demonstrate abstractions everywhere. All right. So in terms of mathematics, let's think of something else. Number. What really is a number, right? So let's say, think of any number. Let's say 3. What is 3? Really, have you ever thought of it? What is 3? It's actually a symbol, right? It is, remember, it's not a number. It is a symbol for a number. A number is nothing more than a concept. 3 is a symbol for a number, which is defined as, very roughly speaking, inductively. There is something, you have one thing, you add another thing to it, it becomes 2, then you add another thing to it, it becomes 3. So sort of it has an inductive definition. But nevertheless, the point here is that this thing 3, that is a number, is nothing more but an abstraction. All right, so let's keep going and let's think of abstractions further. So you would have used or you would have come to know of the concept of abstraction in many other places. So let's say in computer science, in software, can you think of some abstractions? It's a very useful concept in computer science too, because uh, it it lies at the crux really of computer science and mathematics. So let's say we have a function, let's say for returning the square of an integer, right? So let's say I'm using C style syntax. Let's say its name is square, and it takes an integer as an input, integer n, and let's say this is a function, and whatever is its implementation, we don't really care as long as the implementation is correct and somebody has done it, whether it's us or anybody else. But the power that defining a square function this way is in its utility. How is that? Let's say I could write another function. Let's say some special function. Let's say its name is sp. It also takes, let's say, an integer amongst other things. And what I do with it is I write some of my own logic here, do something, then I call this other function which I have written earlier. And what is it? I just call it by its name, which is a square. And let's say I pass in a specific value, square of 4, and I return it in some local variable here. So you see the power. This is the power of the building blocks, how they stack up, how they enable us to make further higher level constructs, powerful constructs. And the key thing here is that when we are defining this function sp, we don't really care how this function square is implemented, right? Because once it's implemented, once we have a name for it, it is an available building block or an available abstraction, which can then be used further to build further abstractions, so on and so forth, to build complicated stuff, right? So the same analogy goes for, it's the same concept that we have discussed. You can, for class names, in object-oriented programming, it's really the same. These are nothing else classes and class hierarchies, but a sequence of abstractions, right? So let's think more about the concept of abstraction. So you would have heard it in other ways as well, but when you think about it, they're all abstractions. So what could those ways be, right? Interfaces, right? So an interface, you could have an interface, an API, which is an application programming interface. A function is an API. Um, a function is an API. Let's say the definition of a service-oriented endpoint is an API, and so on and so forth. API is an interface point, and we can call it as a promise as well, which is a concept that is there in some of the programming languages. But in its essence, what are these really? These interfaces, APIs, promises, these are all names that we call abstractions, right? So when we say we call a function, let's say length of string, let's say there's a function named strlen, and what it does is it computes the length of a string. Let's say s is the string, and it returns back the length as a positive integer, right? So let's say it returns back the result as integer. So what is string length really? It's an interface, it's an API, it's a name of a function, it is an abstraction, right? API could be different. Like, for example, it could be a SOAP API, you know, anything really. Think of any API, any of any kind, right? It is basically nothing more but an abstraction. And for example, and the same, you can, it's virtually the same thing as a promise in this context. So how is it really a promise? It's a promise because there is an abstract entity called string length. It is a function, and it's a promise to its caller, whoever chooses to call this function. It's a promise that if you call me with these parameters, this is what I will do, right? Fundamentally, that's all there is to it. So why are we mentioning all of this? Because we have to be aware of the concept of and its power. So, and this is how we, the humans, we think, we make complicated stuff, because we have the power of abstract thinking, right? This is a key element of uh, our humanness, right? Our power and everything, all kinds of powers that we have, the ability to build complicated things, the ability to solve problems, basically is in a sense fundamentally derived from the power of abstract thinking, right? The ability to think of concepts, to name the concepts, and concepts, then what you do, you name the concepts, and then you forget its details. You name it, you realize it or implement it as part of its definition, as part of giving it a name, and then you forget the details, right? You forget the details of the concept. For example, the analogy is the mathematical function that we talked about or the programming function that we talk about. You forget details. And then what you do is you use this by name or some kind of a handle, which typically is a name, to build further complicated concepts, build more concepts like higher order functions, um, etc., like frames from pixels, videos from frames, so on and so forth. So this is a very, very essential human capability. Now, how is it used really? Well, let's see. It is used, as we have seen, as part of design, as part of designing and building complex things, functions stacked on top of functions, you know, to design. We cannot design effectively unless we abstract things out, right? And number two, we use it, the same power, to model and to understand the real world. Model and understand the real world. The capability of abstracting things out is of fundamental importance in order to model and understand the real world and to use that understanding to solve problems. For example, what could be an example of it? Let's say we have a tree, right? Let's say this is the tree. These are its roots. Pardon my poor drawing, but just to give you an idea. Let's say this is a tree. It has all these leaves and stuff. So let's say if it has a main trunk, this thing, this part, we could model it as a cylinder, right? A three-dimensional cylinder. But in order to have a concept of cylinder in place, we need to understand the concept of a circle, because the circle continued in a dimension makes a cylinder, right? In order to have the concept of a circle, we need to have a concept of a point. Because what is a circle really? It's a point moving, 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 while remaining equidistant from another point, which is at center. And then you keep on building, move, 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 add more points, and it becomes a circle. See how this stacks up. So, to conclude, what I would like to say is that abstractions are a very fundamental concept in computer science, mathematics, and life, in designing software, in designing mathematical entities, and also in modeling and understanding the real world. I hope this was useful. Hope to see you in another, at another time with something else. Bye.